Across modern enterprises, AI agents are moving out of the lab and into live production. Departments like IT, HR, and sales are deploying autonomous models to execute workflows and interact directly with legacy architecture. This rapid adoption creates a management crisis. As deployment scales, the primary bottleneck shifts from the technical challenge of building agents to the systemic difficulty of governing them. When agents are deployed without central oversight, they typically run on shared credentials. They are granted over-permissioned access to systems just to ensure the integrations function, creating invisible pathways into critical infrastructure. These autonomous models can execute sensitive data actions, such as modifying financial records or exporting employee data, without human approval, leaving behind vulnerabilities that are almost impossible to trace. Companies want the operational efficiency of AI automation, but to prevent total chaos, security teams are forced to step in and block adoption entirely. Solving this requires a specific architectural standard, a unified operating layer that sits directly between these autonomous agents and the business systems they are trying to access. This architecture diagram illustrates the requirement, fusing an integration platform, or iPaaS, with strict security governance. iPaaS is a suite of cloud services that enables the development, execution, and governance of integration flows, connecting any combination of on-premises and cloud-based processes. Instead of treating security as a secondary concern, this central hub applies distinct, color-coded cryptographic keys to every single agent pathway, establishing identity and least privilege at the start of the process. To be effective, this control plane must manage the entire lifecycle of the agent across 4 distinct stages: build, connect, run, and govern. By implementing this architecture, enterprise security stops being a barrier to AI and becomes the primary enabler of it. The first layer is embedding security into the agent's initial creation. A geometric boundary shield forms around the agent node, representing construction guardrails. Next is identity. An alphanumeric tag embeds into its core, ensuring every action is traceable to its origin. Next, the system applies the principle of least privilege. The agent is strictly configured with only the exact permissions required to complete its specific task. To protect the model's core instructions from external manipulation, engineers apply prompt hardening, creating strict boundaries around how the agent interprets outside text. The build process requires secure third-party dependency checks, preventing inherited vulnerabilities. Finally, output schema validation applies. Data leaving the shielded node passes through a rigid template, and any unexpected parameters are immediately discarded. When an AI model is constructed with these physical guardrails, it cannot easily be manipulated into executing unauthorized tasks. For organizational onboarding, pipelines extend outward from the shielded agent node toward live enterprise endpoints. Before attaching, the agent's machine identity syncs with the central directory, mapping it directly into the existing identity and access management system. Access to highly sensitive data is never automatic. The control plane enforces strict connectivity approval workflows, requiring explicit authorization before querying restricted environments. The platform then applies IP restrictions and network allow listing, securely confining the agent's operating environment to a set of trusted network coordinates. Finally, administrators enforce strict resource quotas. They set hard limits on token usage, memory allocation, and maximum allowed runtime per session. Secure onboarding guarantees that an agent can only operate within predefined, IT-approved digital boundaries, permanently eliminating the risk of shadow integrations. The third layer is runtime protection. During execution, the agent's workflow is a high-speed data stream. The control plane meticulously intercepts and inspects every packet. This starts with data loss prevention, or DLP scanning, a process ensuring that sensitive data is not lost, misused, or accessed by unauthorized users. Simultaneously, real-time detection engines analyze the traffic, constantly monitoring for prompt injection attacks or attempts to bypass the established guardrails. The platform also enforces time-based operating windows, explicitly restricting the hours when specific agents are allowed to act. To prevent data exfiltration, the control plane cross-references traffic against threat intelligence feeds, actively blocking any suspicious outbound communications. For high-risk actions, a data packet halts at a physical toll gate on the network pipeline, requiring a human-in-the-loop manual approval signal to proceed. If an agent behaves unexpectedly, administrators trigger an immediate kill switch. The toll gate slams shut, completely severing the connection. This active runtime protection ensures that even if an agent's logic fails, its actual physical actions remain strictly bounded by enterprise constraints. The final layer manages these models as permanent enterprise assets. An overarching surveillance grid drops over the network, providing post-execution governance. For every agent action, small data nodes drop into a centralized, locked ledger, creating complete, immutable audit logs. These logs are streamed directly into the enterprise's Security Information and Event Management System, or SIEM, which aggregates and analyzes activity across your IT infrastructure. The control plane manages end-of-lifecycle processes. When an agent is decommissioned, the system terminates its session and executes complete memory sanitization, permanently preventing data recovery. Centralized governance transforms autonomous AI actions from invisible events into fully traceable, auditable records. Comparing the architecture we just built against other AI security platforms on the market reveals a clear categorical distinction. Many emergent AI security tools are designed strictly for the Security Operations Center, or SOC. A SOC is a centralized facility where an information security team monitors and analyzes an organization's security posture on an ongoing basis. We can visualize this distinction on a scatter plot matrix. The x-axis measures the use case scope, from alert triage to full enterprise execution, while the y-axis tracks the target buyer, from the SOC up to enterprise IT. As data clusters populate the graph, we see siloed AI tools grouped in the bottom left, serving security teams for specific tasks. The top right quadrant represents a true control plane, a massive operational hub built for the entire organization. Secure AI scaling requires an operational layer integrated into the core business architecture, serving every department as shared infrastructure, rather than functioning as a specialized security utility. Ultimately, a secure enterprise agent platform acts as the CISO's insurance policy for widespread AI adoption. This architecture allows engineering and operations teams to ship new AI workflows faster because they are building on top of pre-approved, secure infrastructure. It achieves this by unifying agent orchestration, system integration, and zero-trust governance into a single, seamless operating layer. By utilizing a secure lifecycle management platform, enterprises can finally deploy AI agents into production safely, traceably, and with absolute accountability.